So today we will go for the voltage follower. So the voltage follower. So you can easily see the what is mean by voltage follower. You can easily match a source of very high impedance to a load of low impedance. Okay. So this is the inverting, which is fed back to the output of the operational amp. You can see here. Whereas the non-inverting terminal, which may have the source is the input voltage we are going to be giving out, and we are taking the output voltage lines. That means here the output voltage, which is approximately equals to the input voltage. Okay, so you can easily observe that what is going on here. And the entire output voltage here, which is fed back into the inverting terminal, and the input signal which is connected to the non-inverting, whereas the V plus, which is VA is V plus, VA is which is approximately equals to the output. So that's what it is going to be calling as here voltage follower, because five back. So the output voltage, which is always equal to the input voltage. And here this configuration, which is similar to that of the emitter follower, okay, in BJT, bipolar junction transistor, or else you need to say that this is a source follower in field effective transistor. Why? Because of a large gain, that is A naught, it does not allow in a large differential voltage in this voltage amplifier. Okay. Next is the op amp integrator. Another one, most important is that op amp operational amplifier integrator. You can go for it, the integrator here. The So here the circuit diagram for the op amp here. Inverting terminal, we are giving the input source. The source point here, yes. In place of the impedance as well as the resistor, in the integrator, one of the best, which is nothing but a capacitor, is going to be utilized. You can see here. Okay, capacitor. And the inverting terminal, non-inverting terminal, which is grounded here. Through this only we are taking the, between these two terminals we are taking the output. Input voltage is fed back to. Okay, that is the case. If VA is there, R is there, input current, source point. So you can go for this here. The non-inverting terminal is also earthed here, whereas the inverting input is a grounded. The current I through the R, which is nothing but V by R, and the voltage across the capacitor, which is equals to the output voltage. So you know pretty well the capacitance formula, the ratio of the magnitude of the charge to the voltage, C equals to Q by V. RL, the potential difference between the plates, which is nothing but a here capacitor. Okay, C equals to Q by V, or Q equals to C V naught, or V naught is the output voltage, Q by C. But you know pretty well here Q equals to charge equal. Why? Because of I equals to Q by T. Okay, or Q equals to IT, charge form. Therefore, output voltage 1 by C into in place of Q, but I equals to, according to Ohm's law, V by R. Therefore, this is the input current, this is the feedback current. By substituting, you may get minus V naught equals to 1 by CR into integral VI. But you know, the time constant tau equals to RC. Okay. So which may gives you 1 by T gain of the integral. Next, operational amplifier differentiator. In place of differentiator, capacitance place, which may be occupied as resistor. Okay. But the input here resistance is also there. In place of it, capacitance is to be considered. First of all, you should practice the circuit diagram, then only you can easily understand that. For integrator, what you are considering, for a differentiator, what you are considering. That is the case. Next. Okay, you can go. So the operational amplifier differentiator. In integrator, you can see capacitor and resistor. Whereas in the differentiator, resistor and capacitor. Okay, that is the case. Here, non-inverting terminal which is grounded, whereas for inverting terminal itself, you are giving the signal to it. That you need to understand. So here, the non-inverting terminal which is grounded here, and S point which is a virtual ground. Hence the current through the capacitor. What is the current? Q equals to IDT or else dq by dt equals to I. C into D V by D. Why? Because of Q equals to CV or C equals to Q by. In place of Q, CV, which is substitute. Hey. The current value, IF feedback current. IF is the feedback current. Where is the feedback here? The fraction of the output which is fed back to the input, which is a feedback. That is V naught value. This is not V. But it is slow. So V equals to IR or else minus R into I. Since IF equals to II, in place of IF, we can substitute. Okay. So previously what they asked here, you can easily observe that working of voltage and current power. Most important. And another one is that discuss the action of active integrator and differential. Next is the measuring instruments. There's two types are there. One is the analog measuring instruments, another one is the digital measuring instruments. So in the case of analog measuring instruments, there is a D-Arsenal type of measuring instruments are there. And another one is the PMMC type of micrometer. And iron shunt and multi-range ammeter. And conversion of Arsenal PMMC micrometer to voltmeter. Here is the thing is that micrometer to ampere meter. And another one is the micrometer to voltmeter. Next, micrometer to multi-range volt. Next, series type ohm meter. Next is the rectifier type alternating currents. Next, field effective transistor. Input type electronic voltmeter. And the another one is the differential amplifier balance. So let me go for the introduction of this portion. That is the constructional details. So the construction details of PMMC type of OC micro ammeter. Micro means 10 power minus 6 amperes. Is the basis for the almost all positive passive measurements like voltmeter, ammeter, ohm meter. These are the passive instruments. So this may be improvement in accuracy measurements. And this can be achieved by the use of the field effective transistor input type of measuring. Next, the basic movement of DC ammeter is PMMs. So the coil, which can be carried only by the very small currents of few tons of microamperes. So an ammeter which is connected always in series with the load of limiting currents, so DC voltmeter measures the potential difference between 2 points in a DC circuit. The multiplier resistors, which are usually mounted inside the case of voltmeter. You can easily see that D-Arsenal type measurement instruments. So this question is asked so many times. D-Arsenal type measuring instrument. So this is a D-Arsenal type of suspension galvanometer. What is the use of the actually use of the galvanometer is that here to measure the sensitive current. There itself you are going to be using the galvanometers. Okay. But for a few milli to micro ampere of current, there itself you are using the ammeter to measure the current. But the thing is that less than that, for a sensitive current, you are using the galvanometers. So in such a way that here one type of instrument is there. That instrument is the uh, de-arsenal type system. Let me go for the here. It is designed on the principle of PMMs. That is permanent magnet movement coil. Okay. So that is a permanent magnet moving coil, PMMs, type of suspension galvanometer. Permanent magnet moving coil. So whenever a coil is going to be suspended in the magnetic field of a horseshoe type of permanent magnet. So where is this horseshoe type of magnet here? This is the horseshoe type. The coil which is suspended in it. Then the deflection is going to be developed. That means the coil which is going to be interacting. You can write it down. I will give you that question to first page of this. So here there should be a electromagnetic torque which is going to be developed between this. So the electromagnetic torque counterbalanced by the mechanical torque of the controlling springs which are attached to the movable coil here. Where are these? Here. Okay. So the balance torque, the angular position of full coil. By a pointer against the fixed reference here. So the equation for the tau equals to BA again, cos t, sin theta. The restoring mechanical torque. Suspension springs try to counterbalance by rotating. Tau equals to C theta. Okay. So in tau is nothing but here torque here. B the magnetic flux. A the area of the coil. I the current which is in the movable coil. Capital N are the number of turns on the coil. Capital C the restoring couple for unit rotation exerted by the mechanical suspensions. Theta is the angular deflection. Okay. The more deflection, more current. That's what here I is proportional to theta. More current, more deflection. Less current, less deflection. Okay. So that's what here BIAN, which is equals to tau, that is approximately equals to C theta. Okay. So you can see here this sentence is very the current flowing through the coil which is proportional to the deflection of the coil. Next, de-arsenal PMMs type micrometer into ampere meter at high ranges. Micrometer to an ampere meter. Okay. So here the coil which can carry only small currents, that is approximately equals to few tons of microamp. Whenever a large currents are to be measured, it is necessary to be bypass the major parts of the current which can through the shunt resistance. So the resistance of this shunt can be calculated. by the conventional circuit. Here there is a RM internal resistance of the moving coil, and RS is the resistance of the shunt, and IM is the full scale deflection current. IS is the shunt current here. I is the total current. So formula, if it is a shunt resistance which is parallel with the micrometer, then the voltage drop across the shunt and movement must be same. In this particular case, V shunt equals to V movement. You know pretty well according to the Ohm's law, V equals to IR. That's what VM equals to V shunt equals to ISRS. VM equals to IMRM. Whereas RS equals to IMRM by IS. But I equals to IS into IM. Substitute here. IS equals to I minus I. So that's what this is the case. RS equals to IMRM by IS. Okay. Micrometer to here a ampere meter. How to convert it? Next is the aeroton shunt and multi-range ammeter. So the current range of the DC ammeter, which may be extended by the providing a large number of shunts by a range switch. This is the schematic diagram of a simple multi-range ammeter. And this is the universal or aeroton shunt. So what are the shunts here? 4 shunts are there: RA, RB, RC, and RD, which can be replaced by a parallel with the movement to give 4 different ranges. So switch S is a multi-piston, where it is this one, and make or break the type switch. If you want to connect it here or else here or here, whatever. 4 different places are there. Okay. So the problem which is associated with this type of circuit is the DC meter. It is not protected with the current ranges. So here this universal or return shunt, which can eliminate the possibilities having the meter in the circuit without a shunt. So the what is the disadvantage which can be gained by the piece slightly or higher overall the meter resistance? Shunt at any achievement piston. Of the switch of any one of the shunt resistance. See here, it may switched by the any of either 4 are there. Out of this, it can be connected to either RA, RB, or RC. So these calculations indicating a large currents, the value of the shunt resistance may become very small. DC current ammeters. Ranges which are available from 20 microampere to 50 ampere, full scale. And 50 to 5 to 500 amperes. So precautions also there, different precautions while you are going to be performing or to be utilizing this ammeter in a circuit. There itself you need to follow the such a precautions. So these are the precautions. But in examination they won't be asked here what are the precautions here. But you need to understand that here what are the precautions to be taken place while you are connecting the circuit. Next is the conversion of AD adversary. PMMC type microammeter volt. So the addition of series resistors or the multi-layer which may converts the basic DR to DC volt. So the current through the movement so as not to exceed the value of full scale deflection current. A DC voltmeter measures the potential difference between 2 points in a DC circuit, therefore, which is connected across the source of electromagnetic force EMF or in a circuit component. Then this meter terminal, which are marked as the plus or minus. So the value of multiplier series resistance required to convert a microammeter into a volt. V equals to Im into Rs plus Rm. But Im into Rs equals to V minus Im Rs. Calculation. So Rs equals to V minus Im into Rs by Im. Here Im get cancelled, only Rm is. So this is the multiplier. Rm is there. Yeah. So what it is? The terminology is related to it is Im is the deflection current of the movement. That is IFS. Rm is the internal resistance. Rs is the multiplier resistance. V is the full range voltage of it. Next is the conversion of microammeter into multi-range. Micro-range ammeter, multi-range voltmeter. Multi-range voltmeter. Okay. In place of switch, V1 voltmeter, V2, V3, V. Here the current. So whenever you are going for a new concept here, you must know the what is the previous one and what is the present. If you correlate with each other, then only you can able to understand the present scenario. Okay. So that is the case you may be observed in the case of this. So a multi-range voltmeter using the 4 piston switches for 4 multipliers. That is R1, R2, R3, R4 for V1, V2, V3. Next is the conversion of microammeter into series type ohmmeter. Series type. Completely all are resistors. R1, R2. Here RK, RM between A and B. Bad. So this is essential, which may consist of d-arsenal movement connected in series with the resistance and battery to pair a terminal to which the unknown resistance is connected. That is Rx1. Unknown resistance in series. So what is the current through it? Which may depends on the magnitude of unknown resistance. Here there is a meter which is indicating which is proportional to the value of unknown resistance. That is, if it is Rx value between the terminals A and B, if it is 0, the maximum current which may flows through it, and the shunt resistor R2, it may be adjusted until the moment of indicates full scale current FST. If it is 0 ohms, if Rx is infinity, then there is a circuit drops to 0 and the moment indicating here 0 current. Then it is to be marked as a infinity here, like that. R1 is the current limiting resistor. R2, which is zero adjusted resistor. You can easily adjust this. E is the internal battery. Rm is the internal resistance of D arsenal. And Rx is the unknown resistance. So by these resistors, you want to calculate the I values of scale deflection. For different solutions. So like that, you can easily calculate the I values. And by doing these equations, E and V both are equal. Okay. So that V value is also going to be. Substituting, you may get the this one. Okay. Next is the rectifier type AC currents indicating system. So the D arsenal moment response only to the average or DC current value of the current through the moving coil. If the current movement, if the movement carries the alternating current with the positive, negative half cycles, that is AC. Okay. The driving torque would be in one direction during the positive half cycle, and for the negative half cycle in the other direction. So the frequency of the AC is very low. So the pointer would be showing back and forth around the 0 point on the meter scale. That for higher frequencies, the inertia of the coil, which is so great as the pointer cannot follow. The rapid reverse of the driving torque and how it is going to be entering into the 0 mark. So the RMS value of the current value, IRMS equals to I maximum by root. And DC value 2 by pi into I max. This is the case. So bridge rectifier. Diodes are to be used here. And IDC value and IRMS value. Full wire it. So the bridge rectifier which may produce the pulsating unidirectional current through the meter movement over the complete cycle of the influence. Because of the inertia of the moving coil, the meter will indicate steady deflection, which is proportional to the average value of the current. So here the currents, alternating currents as well as the voltages, which are usually expressed in RMS values, root mean square. The meter scale is calibrated in terms of RMS, sinusoidal wave. Okay, AC is a sinusoidal wave. Sinusoidal waveform which may have the positive half cycle as well as the negative half cycle. I think you know that. Next is the last one, FET input type electronic voltmeter. FET means field effective transistor. So do you notice it that each and every concept which may have at least two circuit diagrams, okay? One or two circuit diagrams are there. So you need to do practice. Without practicing these circuits, you cannot able to remember all these. Okay, that's what you need to go for the thoroughly you can practice, then you can easily understand. So in electronic voltmeter circuit with the field effective transistor, a simple amplifier type electronic volt. This is the here a DC input voltage. See here, positive terminal, negative terminal. Three resistors are there. One is the 9 mega ohms, 900 kilo ohms, 100 kilo ohms. Voltage is three voltages. One is the 0.5 volts, 5 volts, 50 volts. This is the range here. This is the 1 mega ohm. And this is a FET here. Drain gate source. Okay. Drain source gate. So this is the transistor, NPN transistor. And a variable resistor. There is a current, that means deflection you can easily observe it. So this is the switch here. At output, this is a 4.5 volts. Very, very less. Okay. So a source that is this which can reduce the amount of power drawn from the circuit under test by increasing the input impedance using an amplifier with unity gain. A source follower drives an emitter follower, and this combination which is capable to achieve 1000-fold increase input impedance, while it is going to be maintaining the voltage gain which is nearly 1. The input impedance of this meter is 10 mega ohm, 10 mega ohms, which it required 0.25 microwatt of power for 0.5 volts difference. Compared up to 25 micro watt per passive meter. And an increased sensitivity of 100 times, which is achieved through the. So here there is a emitter follower, which must have the current present and the emitter voltage none not go to with the zero input voltage. Next is the differential amplifier balanced bridge type electron. See, this is the one of the most versatile general purpose measuring instrument capable of measuring DC and AC voltage as well as the currents and resistance with a solid state electronic multimeter or VOM. Although the circuit details vary from one instrument to the next. Then అయిపోయింది. 10 రూపాయలు. So here there is a balanced bridge DC amplifier indicating meter. There is an input in attenuator or range fix rectifier section which can convert the AC into DC. Rectifier AC to DC function switch which can select the measuring the functions of instrument such as voltage or current or resistance or DC or AC. Here there should be a BJT is also bipolar junction transistors, two-way. Yes. So in this, give design consideration for converting D-Arsenova type PMMC meter into this. PMMC meter into voltmeter. One is the ammeter, another one is the permanent magnet Mori coil. Moving coil. D-Arsenova is the name of the sign to design the PMMs. So by tomorrow, we will discuss. This is the analog one. Okay. D-Arsenova type. PMRs. Digital measurements also there. These are the digital. So by tomorrow's class, we will discuss about the digital voltmeter and classifiers. DVM. Okay. Right. Thank you.
स्पीड में नजर आने वाला शख्स
So by tomorrow, we'll discuss digital voltmeters, DVMs. Okay. Today we have been completed analog one. Tomorrow's is digital one. Right. Thank you.